String theory is a fascinating area of physics. It seeks to answer some of the biggest questions about our universe. At its heart, string theory is a theoretical framework that replaces the idea of point-like particles with one-dimensional vibrating strings. Imagine these strings as incredibly tiny, elastic bands that vibrate in different ways. These vibrations, according to string theory, are what give rise to all the different particles and forces that we observe in the universe. The ultimate goal of string theory is to become a theory of everything. This means it aims to provide a single, unified description of all the fundamental forces of nature, including gravity, electromagnetism, and the strong and weak nuclear forces. Currently, our understanding of the universe is fragmented. We have the theory of general relativity, which describes gravity and the large-scale structure of the universe. On the other hand, we have quantum mechanics, which governs the behavior of matter at the subatomic level. The development of string theory has a rich history. It was initially explored in the 1960s as a way to understand the strong nuclear force. However, it was later realized that string theory had the potential to be a much more fundamental theory. This realization sparked a flurry of research, leading to the development of superstring theory, which incorporated the concept of supersymmetry. Over time, 5 different versions of superstring theory emerged, each consistent in its own way. In the mid-1990s, a remarkable discovery revolutionized the field. Physicist Edward Witten proposed that these 5 seemingly distinct superstring theories were actually different facets of a single, more fundamental theory called M-theory. This breakthrough ignited what is now known as the second superstring revolution. M-theory operates in 11 dimensions, one more than the 10 dimensions of superstring theory, and it suggests the existence of even more extended objects called branes. At the heart of string theory lie, strings. These are not the strings you might use to tie a knot. Instead, they are incredibly tiny one-dimensional objects that vibrate in different ways. Imagine them as the smallest possible vibrating rubber bands. Each vibrational pattern corresponds to a different type of particle. Just like a guitar string can produce different notes depending on how it vibrates, a string in string theory can manifest as an electron, a quark, or even a graviton, the hypothetical particle that carries the force of gravity. One of the most mind-boggling aspects of string theory is its requirement of extra spatial dimensions. While we experience only 3 spatial dimensions, length, width, and height, and 1 dimension of time, string theory suggests the existence of additional dimensions, curled up and hidden from our perception. These extra dimensions are not just a mathematical quirk, but are crucial for the mathematical consistency of the theory. To visualize this, imagine an ant crawling on a very thin hose. From a distance, the hose appears one-dimensional. However, the ant can move along the hose's circumference, an extra dimension, in addition to moving along its length. String theory also introduces the fascinating concept of dualities. These are mathematical connections between seemingly different theories that reveal them to be equivalent descriptions of the same underlying physics. One example is T-duality, which relates string theories compactified on circles of different radii. This duality suggests that a string theory with a small compactified dimension is equivalent to another string theory with a large compactified dimension. M-theory, the 11-dimensional theory that unifies the 5 superstring theories, is a central pillar of modern string theory research. It proposes the existence of objects called branes, which are higher dimensional generalizations of the strings themselves. Branes can have various dimensions, and they play a crucial role in understanding black holes and the early universe in the context of string theory. String theory has provided valuable insights into one of the most enigmatic objects in the universe: black holes. Black holes are regions of space-time where gravity is so strong that nothing, not even light, can escape. Stephen Hawking's groundbreaking work in the 1970s showed that black holes are not entirely black, but emit faint radiation due to quantum effects near their event horizon, the point of no return. String theory offers a way to understand the microscopic origin of this radiation, known as Hawking radiation. According to string theory, black holes can be thought of as a highly excited state of strings and branes. The vibrations of these strings and branes at the event horizon give rise to Hawking radiation. Moreover, string theory provides a way to calculate the entropy of a black hole, a measure of its internal disorder, which had been a long-standing puzzle in physics. One compelling example of string theory's success in explaining black hole phenomena is its application to a specific type of black hole called a 5-dimensional black hole. By considering a particular configuration of strings and branes in 5 dimensions, string theorists were able to reproduce the precise formula for the entropy of this black hole, matching the prediction from classical general relativity. This remarkable agreement provided strong evidence for the consistency of string theory and its potential to unravel the mysteries of black holes. Perhaps the most ambitious goal of string theory is its quest to unify physics, to find a single theoretical framework that can describe all the fundamental forces and particles in the universe. The current state of physics is marked by a divide between general relativity, which governs the universe on large scales, and quantum mechanics, which reigns supreme in the microscopic world. String theory, with its potential to unify gravity and quantum mechanics, offers a glimmer of hope for bridging this gap. One of the most profound developments in modern string theory is the ADAS-CFT correspondence. This remarkable duality, discovered by Juan Maldacena in 1997, posits a relationship between string theory in a particular spacetime called anti-de Sitter space, ADS, and a specific type of quantum field theory called conformal field theory, CFT, defined on the boundary of that spacetime. In essence, it connects a theory of gravity in a higher dimensional spacetime to a theory without gravity in a lower dimensional spacetime. The ADAS-CFT correspondence has far-reaching implications for various areas of physics. It has provided insights into the behavior of strongly coupled quantum systems, such as the quark-gluon plasma, a state of matter thought to have existed in the early universe. Additionally, it has shed light on the nature of black hole information paradox, which questions what happens to information that falls into a black hole. The ADAS-CFT correspondence suggests that information is never truly lost, but is encoded in the quantum state of the Hawking radiation. In conclusion, string theory, though still under development, represents a bold and promising attempt to unify physics and unravel the deepest mysteries of the universe. Its concepts of vibrating strings, extra dimensions, and dualities paint a captivating picture of a reality far richer than our everyday experience. While experimental verification of string theory remains a formidable challenge, its elegance, mathematical consistency, and potential to connect seemingly disparate areas of physics continue to fuel the imagination of physicists and inspire the quest for a complete understanding of the universe.